All right, I got 2:30. Let's go ahead and get started. Any questions that anyone has to ask before we get going? No?
I have a question, but the second to mark down as Wednesday, March 16th.
Cool, March 16th. Thank you, Isabel. Is that the week after spring break? Yeah. Sorry, I had nothing to do with that day. All right. So just to kind of recap, this is where we left off last time, this idea of this ladder being pulled down a wall. We're going to stick with this scenario and ask ourselves a little something different. So same thing, I mean, the same physical behavior is happening in pulling this ladder down the wall at a constant rate, but now I'm interested in different stuff. So what rate is the angle between the ladder and the ground changing when the base is 8 feet from the wall? So I'm going to recreate my diagram the way we had it before. Hopefully more triangular this time. So that ladder is 25 feet long. And even though this is the same situation, we should probably think about what the variables are again. So what variables are at play here? Is there anything from last time we can steal and reuse here?
Time seconds.
Time is, so what sets you out there? Why do you think I can use that again?
Rate.
Go a little deeper, because I can think of lots of rates that don't necessarily involve time. Is there anything else in the way this is written that tells you that time is something I should pay attention to? Yes.
It says feet per second.
Yeah, so I'll give you a rate in feet per second. So per second tells you that time is kind of my governing quantity here. So as time changes, other things are going to change. What of those other things should I be interested in? What did we look at last time? In addition to time, Isabel?
The distance that the two sides were changing.
So we looked at both distances, right? The horizontal and the vertical distance. Should I look at both of those this time again? One or the other? Let's take them one at a time. Is that horizontal distance from the foot of the ladder to the base of the wall along the floor? Do I care to look at that distance again? Or should we back up even more fundamental? What changed? What did the situation changed from Friday to today?
You went from looking like the height of it sliding down to now you're looking at the angle.
Which angle am I looking at?
Between the ladder and the ground.
Okay, so let's mark that angle. And let's give it a name. Okay, this sounds good. So we care about that angle, right? So if we care about that angle, I think that's a good variable to look at. So angle, and we'll say angle as shown just to save myself on characters. What's a good unit for that? Degrees would be good. I'm gonna force us to radians, but better be an angle measure of some sort. So I'm looking at time. I'm looking at that angle which we call theta. What other quantities do I need to look at? Anything? How am I defining that angle? Or where does it exist? Could I have drawn theta up at the top of that triangle? I think that would have been not in the spirit of what I'm asking here. So why did I have to draw it where I did? Good.
Because it's asking between the ladder and the ground on the wall.
So it's between the ladder and the ground, right? So why don't we do this? Why don't we start thinking about, so we got the time variable, we got that angle variable for theta. But we should look at, you know, what are we eventually going to want to solve for, Isabel?
We probably want the distance. I can't use words today. You want the horizontal distance?
Okay, what do you want to call it? D? Okay, why do you think we want that distance?
Because we're gonna use cosine.
Okay, so you're looking at how we're going to set this thing up. And yeah, now let's, if we're going to talk about setting up an equation that involves an angle, hopefully, and at this stage, maybe you didn't, and that's okay. You're still kind of getting used to it. But if we're going to start looking at the rate of change of angles over time, or really anything involving an angle, probably need to set up some kind of a trig equation. So D is the horizontal distance as shown. What's a good unit for D? Okay. All right. Is there anything else we can look at? What am I being asked to find? Either tell me in English or give me a mathematical notation based on it.
Theta would be equals 8 feet.
I'm looking for theta when D equals 8 feet. You're so very close. I agree that yes, D equals 8 is the key moment to focus on. I don't think it's strictly exactly theta we're looking for. What does theta tell you? Like, what does theta stand for? It's just what the angle is, right? Am I looking for exactly what the angle is?
Looking to change.
Looking for the rate of change of the angle, right? So what's the thing I'm really looking for?
D behind there. Theta.
You're getting on the right track. I'm going to call it d theta dt. Just to kind of unpack that notation again, d theta dt is basically what this says right here. Well, the rate at which the angle between the ladder and the ground. So all that long phrase right there is just what we call theta, right? The angle between the ladder and the ground. The rate at which that is changing. Didn't say anything about time in there, but it's implied. So we're looking for this d theta dt. And I'm going to forego writing out what its definition is because we have a good definition for t, we have a good definition for theta, which means d theta dt can only be the thing that, you know, mathematically is describing that rate. So I think we have a good list of things that the information that is captured here. Now we got to put that equation together to pull all those things together. So I want d theta. I want to somehow involve these quantities. Kind of already hinted at it, but we want some sort of trig equation. What would be a good trig equation that links those things together? I have my angle, I have two sides of a right triangle. Based on the two sides of the right triangle I have up there, which trig function is the one that makes sense as well? Cosine, I got the adjacent side and the hypotenuse, right? All right, so I need a cosine. Cosine theta equals what? Garrett,
G over 25.
D over 25, right? And just to get away from fractions, I'm gonna rewrite like this. D equals 25 cosine theta. All right, so I have an equation. I want to somehow get to d theta dt, right? So what can I do with that equation to start marching towards the rate d theta dt, the rate that I want? Does my equation that I have written as it stands involve time?
No,
No. So how do I get there?
change the D to involved with 2T.
I don't think we can. Can't say d equals 2t because that means isn't d. We can't assume that we knew where the word began, right? So I don't know if we can go the route of coming up with some function for d that's in terms of t. But think about what we did last week. How did we get time involved in this situation here? So even though it's not there, we can differentiate both sides of this equation with respect to time, right? What is the derivative of d with respect to time? And we don't really know, but I can give it this name, right? Basically, what is the rate of change of that variable d with respect to time? Well, by definition, that would be called d dt. We'll worry about it if we know what that is later. But for now, we can leave it at that. What's the derivative of 25 cosine theta with respect to t?
Negative.
Negative 20 sine theta.
Negative 25 sine theta. There's one more thing that has to happen.
Theta prime.
Times what?
Theta prime.
Times theta prime, which I will write as d theta dt. So I have not represented this way yet, but basically what you're doing here is, at least maybe I'll show what I did with the theta term on the right here. This d dt of 25 cosine theta ends up being equal to this. Is equal to dd theta of that term times d theta dt. So, and that's kind of what the chain rule always says, right? You differentiate something, differentiate the outer function with respect to whatever its input variable is, and then you move one layer inward and take the derivative of that function with respect to that its input. So are we okay with this derivative here? We got d theta dt. So I think we'll be able to solve for this thing if we know all the other pieces, right? Do we know d dt? Let's ask this more basically. Based on that notation, what does d dt have to mean? It's what rate? So many variables to look at. Garrett? Why would it be 2?
Because it's the difference in D in relation to seconds.
Right, so it's, think about what that notation d dt means. It's how fast d is changing. What does d stand for? It's that horizontal length along the floor. How fast that distance is changing with respect to time. We have agreed that that is 2 feet per second. Equals negative 25 times sine theta. Is there a way for me to find sine theta? What else do we know about this ladder right now? Like at the instant where I actually care about it. Garrett?
It's at 8 feet.
It's what?
It's The base is 8.
The base is 8, right? So let me draw a second triangle up here. What is that? So I know the hypotenuse is 25, and I know the base is 8. Couldn't I find the opposite side? If memory serves from last week, it was like 23.8. So from there, I think I can say this: the sine of the angle is 23.8 over 25 times b theta dt. Any questions here? I don't think we should get a final result. Just 2 divided by 23.8. I'm getting negative 0.084 radians per second. Does the negative number make sense? So if you're pulling the ladder away from the wall, I think the angle will be shallower. Any questions here?
Yeah,
Go ahead, Joshua.
when it goes from 25 cosine theta to negative 25 sine theta times d theta dt, why is it not just negative sine theta if you're taking the derivative of 25?
So you're taking, remember that 25 is, it's not like, it's a constant, yes, but it's multiplied by the variable function. It's not added to. If it was 25 plus cosine theta,
And it would be 0.
then the derivative, then you're taking the derivative of 25 all by its lonesome, and that would be 0. But this 25 is not really a constant in the same way. I mean, it's basically just kind of increasing the amplitude of that cosine function. So because it's increasing the amplitude, it's increasing the rate of change, which is why the derivative is 25 times as big as what the derivative of just plain old cosine would be. Good question. Anything else? Okay. Let's do another one. All right. Perfectly spherical balloon is being filled with air at this constant rate. At some point in time, we can measure the radius. So let's do this before we even think about what we want to solve for. What variables are here? What's worth looking at? Here. Time. Yet again. Here it says they're measured in minutes. Isabel?
Volume and cubic inches.
Okay. Volume of what?
Volume is square root of
Okay, so volume. The balloon, you said that was in inches cubed. What other ideas are here? There's time, there's volume. Or is that all? Isabel?
I want to say that there's also just not surface area, but just increasing of like a circle.
So yeah, so you're talking about some kind of we're talking about a shape that's growing, right?
Mm-hmm.
Let me try very badly in 2D, draw a 3-dimensional object. Shaping shows us 3D. Spherical thing, right? It's one thing to say qualitatively it's growing, but how do you describe that mathematically or with with numbers. So yeah, you can say the volume is growing, right? What is the volume of this kind of object depend on? On its radius, right? So I think it's probably makes sense to bring in radius as well. Based on the units you gave me for volume, what unit should I use for radius? All right, I got time, I got volume, I have radius. Is there anything else I should look at? Is there anything else that's mentioned in here? It's probably a good place we can add to it if we discover there are more things we're paying attention to. So now that we have that, what else should we move on to? Is there a way to relate any of those ideas there?
Maybe like CV or VT.
So let's write down dVdt. Based on this name, dVdt, what does that mean?
The rate of change in the volume over minutes.
Over time, yeah, or over minutes, yeah. So that's a good rate there. Are we told anything about that rate? Do we want to solve for it? Is that rate mentioned at all? Here? Yeah, so that's given to us as a constant rate, right? So that's like the rate of change of volume into this, of air into this balloon is a constant 10 cubic inches per minute. So I've got some way to kind of relate the volume of this balloon to time. Let's stick with this first bullet here, or the first of the little sub bullets. What do I want to know? I want to solve for R at some value, right? So we're looking for R for the first part. How do I start doing that? What do I need to start solving for things?
Ooh.
We put together an equation that kind of relates some of these ideas together. So as time goes on, what's happening? The volume of what? The volume, sorry, the volume of what kind of thing? It's a balloon. What shape is the balloon? Do we know anything about spheres that will help us? So we know some kind of formula about it has to do with spheres and their volumes, right? What is that formula? So close.
Oh yeah, R cubed.
Okay, we wrote it down. Now let's think about, is this thing actually helpful? Does it relate any of the ideas that we wrote down before? Yeah, it relates volume and radius. That's good. Does it relate volume to time? Could it?
Yeah,
How could it?
because we have the rate of change for the radius. That relates to time.
You do have the rate of change of the radius at a specific moment. We have the rate of change of volume over time at all the moments. But right now, that equation is not going to be able to speak those languages. It doesn't involve time. So can I modify it or operate it on it in a way that will bridge that gap? Isabel? Take the derivative of it, be more specific. Take the derivative of it, how? Right, but sorry, with respect to what variable? Radius? Yeah, time, right? So that's how you get time involved, right? I can basically, I can take the derivative of both sides with respect to You know, I could do radius, that's gonna leave time out of it still. But if I do the derivative of both sides with time being the independent variable, what's the derivative of this capital D with respect to time? Yeah, by definition, it's ddt. How about this other thing? How do I take the derivative of 4/3 pi r cubed with respect to time?
4 pi r squared times
So you just took the derivative of 4/3 pi r squared, r cubed with respect to what?
to t.
No, you haven't done that yet.
Oh,
Just so to get 4 pi r squared, we took the derivative with respect to what?
oh, respect to the whole r.
Okay, so now, but taking the derivative with respect to r is not how I started this. What do you have to take the derivative with respect to?
T.
Right, so this right here, and hopefully this makes it clear. Let's just finish off what it's supposed to look like. This is dr dt, right? This piece right here by itself is dv dr. So basically what we have is this. dv dt is equal to dv dr times dr dt. Not really a coincidence that it looks like those things will cancel out on the right side. It would just be dv dt. But that is a good derivative of this equation. Any questions there? All right, we want what? Did I ask what we wanted to solve for? Yeah, okay, so, yeah, I think I did. So we want to solve for r, right? So do we know what ddt is? Yeah, it's 10, right? 10 equals 4 pi times r squared. Do I know what dr dt is?
Yes.
1.7. 1.7.
Oh,
Which means you have enough info to find r, which is about 0.684 inches. Any questions there?
So when you say like dV over dt, that's just saying the rate of change, like dV over dt equals, like, means the rate of change of the volume over time. right?
That's it. By definition, that's what the notation does. It's the rate of change in whatever this is, with respect to whatever this is. What I mean, and, you know, the rest of it depends on whatever we decide on the variable. What is the volume of the balloon at that time? Is it possible to find that?
you should have plugged it on.
Yeah, okay, so. Yeah, that once you get that radius, then you can go back to the undifferentiated formula for volume.
4/3 pi r cube.
What's that?
4/3 pi r cube.
Yes. Mhm. So you plug that R value in there, you'll get a volume, which I believe you could get. Let's move on. Before we do at least one more example today, let's just kind of revisit, like, is there some kind of, it's not really a tried and true way to do any of these, but is there a kind of a general process that we follow? What kind of things do we typically begin with? We're thinking about these.
Define variables.
So define all the variables. And just to be clear, like, it's, at this stage, I would advise you, as you're gonna work on the webworks and quizzes and stuff, be really specific about what about the variables you're doing. Just to kind of highlight from Friday, when we were doing that latter one. I mean, said, oh, it's just, that stands for distance, but when we have multiple distances involved, it really pays to keep them all, distinct from each other somehow. Define all the variables. Then what? That's a good step. Garrett?
Define any given rates.
List any given rates. So haven't even tried to solve anything, we're just paying attention to the things we know, which is like hugely important for getting started on these things. There's a lot of things to keep track of. What else? Taking stock of everything you know, listing the given rates, then what, Garrett?
Formal where shape, yeah,
What's that?
like the formal where shape from.
Yeah, so write a formula or equation, right? Won't always be some geometrical thing. But yeah, if you're gonna solve an equation, I don't know how you're gonna do that before you write one. So write an equation down. Now what? What do we pretty much do every time after we write down the equation? Take a derivative, right? This whole section is called related rates. You're not going to get to rates without derivatives, kind of by definition. If you want instantaneous rates. Now you got a derivative, now what?
Solve for the derivative one.
Yep, which I think means we missed something somewhere. So solve for desired variable. I'm going to go ahead and suggest somewhere in here. Determine the goal. I would say figure out what you're trying to solve for, which will probably organically just pop out at you as you're kind of working through these, but now, I don't believe most things in math, including this, have like a tried and true step-by-step process, but kind of a good rough outline to get you started on these. But they can get tricky, as you've seen. Anything else we should add to this before we get going to another example or two? All right. Okay. A plane flying north and a plane flying east. At what rate is the distance between the planes changing after 2 hours have passed? So how do we want to think about this? Garrett? Okay, so we gotta start the variables. Time again. So I'm gonna say time elapsed. Hours is what I'm giving here. As long as we're listing variables, what else is in here?
Distance.
What, okay, what's distance? What is it? Give me a name for it.
Kilometers.
Oh, not like a unit, but like a symbol that I can.
Well, there's two, so it's probably X and Y.
Okay, I'm glad you caught that. So yeah, distance is probably insufficient. So X and Y. So you're calling X and Y, what in your eyes, what is X stand for?
500 kilometers.
Sounds like it's not a variable if it stands for 500.
Yeah, it comes.
Horizontal distance.
Say the horizontal distance. So yeah, I'll say horizontal, or to be clear, the east-west distance. Is this for either plane? I mean, they're, like, they're only one of them traveling east and west. This Y will be vertical then. What are the distances measured in? Here? I thought you had your hand up. So we got time, we got X, we got Y. What else? Or is there anything else? So those are kind of our value, like volume, static measurement variables. Are there rate variables we should think about? So what are some rate variables that kind of go hand in hand with these? Isabel?
500 kilometers per hour.
So let's stop with 500 kilometers per hour.
To the vertical.
So what should I call that thing then? DYDT makes sense for what we've defined. That's a constant 500 kph. Do we have a corresponding dxdt? Okay. All right. Let's keep going. So that's got a good list of, static variables. We know a couple of constant rates. What else are we trying to find out?
The distance,
Oh,
the distance in between them.
okay, the distance in between them. So here's one thing that I also advise we do, even though we didn't do it very early here. Yeah, figure out how to make a message. So based on what you said, I'm going to call this Y. Is the right angle? I'm going to call this X. Is there anything else I should add to this diagram we should think about as well?
I know that it's point that was specifically looking at after 2 hours, so we could calculate the horizontal and vertical distance.
Okay. We could, I'm gonna hold off on that, hold that thought for now, but are there any other variables we should look at? So like, what are we being asked to solve for?
The hypotenuse of them, I guess, right?
We're something having to do with the hypotenuse, right? So we should probably give it a name.
Just
Z seems appropriate. This is gonna be the distance between planes, right? Why do I absolutely need to include this thing? That's part of it. But what does Z have to do with the thing we actually want to solve for?
if it's like for me.
Yeah, so basically I want dz dt, right? I want the rate of change in distance between them. So because let him say this, dz dt is equal to yeah, that's the thing we want to find out. So now based on that, what's a good equation to link all these things together? And when I say link all these things together, I mean, usually the first equation we've written down hasn't had much to do with time, right? And it's not typically going to be the case until you get a derivative. So what are our variables that are not time? X, Y, and Z. Is there any way to relate X, Y, and Z all to one another?
X squared plus Y squared equals Z squared.
Right. Sounds good to me. Pythagorean Theorem. X squared plus Y squared equals Z squared. Keeping in mind that the thing we really want to find is dz dt. So how do we get there?
derivative of both sides with respect to t.
Perfect. What's the derivative of the left side with respect to time?
Two x times dx dt
2x dx dt.
plus 2y dy dt.
Equals what?
Times the dz.
And I'm gonna divide through by 2. So I want dz dt, which means I better be able to find out everything else. I'm gonna compact things a little bit. X prime plus y prime equals z prime. Z prime is the thing, or sorry, z prime is the thing I want to find out. Do I know anything else? Do I know x and y? Do I know x prime and y prime?
Yeah.
What's x?
Would be that
12.
How do you get 1200?
for rate of change is 600 per hour in 2 hours.
Okay. So I agree with that. So I get 1200 kilometers. What's x prime? 600 kph. Not giving up something for them. Oh, by the same token, this is going to be 1000 kilometers. Times 500 kilometers per hour equals. Do I know z? Can we find it? How do we find it? You got Pythagorean theorem, but we based this whole situation on Pythagorean theorem, so we can quickly figure out what the hypotenuse is if that triangle has legs of 1200 and 1000. I got 1562. And dz/dt is the thing we want. So I think we have enough information here to figure out dz/dt. Has anyone already gotten to the end of this? I got 781 kilometers per hour. How are we doing here?
What was the last step you made in order to get 781?
Basically added these two things up, divided by 1560. That comes from Pythagorean theorem. Yeah. So taking x and y to be 1200 and 1000. Yeah. But yeah, x is 1200, y is 1000. Z comes out to be about 1566.
So the 600 and 500, you don't multiply the 1200 and then.
No, so, and that's a good question. Remember what x, y, and z stand for? X, y, and z. What do these three things all measure? Distance. Those are distances, right? So these ideas right here are the relative speeds. So I'm just trying to figure out, so going back to this equation here, I am trying to figure out basically, in order to figure out what Z prime is, I need 5 other pieces of data. I was told X and Y, and X prime and Y prime. I need Z prime, so the missing link here is Z. The only way to get Z is by solving that equation. Okay. And that ends up being 1,562. Anything else about this? Any questions about any of these? Anyone we've done today or on Friday? All right, I have 3:16, but I do not want to start something new in the next 3 minutes. I'll go ahead and break early. Oh, there's one more thing I got to tell you. Sorry. I put an announcement on this right before class started, but I don't think this will affect many of you, 'cause I haven't had a lot of takers, but on Mondays and Fridays before class, I've been coming in at 2 to give help if we needed it. After today, I won't really be able to do that anymore. So I still have office hours Thursday afternoon at 2, Friday at noon. Or you can always set an appointment with me for those other 2 like little half-hour sessions. I'm gonna have to do away with those, but I will always work with you if you need something, just please reach out. Otherwise, have a good day. See you Wednesday.
Are those office hours in this class?
No longer. So my office hours on Thursday and Friday, they're in room 303, which is like just down the hall on the right. So, yeah. So initial identity is, that's my data. So. Yeah. So initial means, that first, so. Now I start to do log. Yeah. So we can't really do this until you figure out what steps. So you're gonna find the initial acceleration here. Yeah. Yeah.
And then I didn't finish.
I only
finished like 4 and people 6. Like I only finished 2 of them because of the.
So this derivative, so your derivative acceleration is 1 plus 110. Yeah. So you will have.
Yeah.
I gotta watch the act.
Thank you.
We did. I heard it was pretty good. You know.
So they don't actually have anything to do with it. So it's just the distances. So.
I didn't even know it was like total score. Okay, I was like,
No, it's so-
It was like according to my grades.
Was it 1,200 times 600? Plus 1,000. Times 500 equals.
Dude, I didn't even watch it in the class.
Instead of writing. Yeah, just if I would have had room, I would have
day, I had
written it out, but
so I couldn't show it. So I showed it, nothing on the screen.
I just have one quick question.
go for
You always have that tattoo?
it. I have,
Just for Arizona?
yeah.
Yeah, that was it.
So you just wanted to clown on my tattoo before you went?
No, I just never noticed it before.
Oh, yeah.
Me neither.
I also have this one. So every year my daughter's birthday.
Age 1.
So I have, they go all the way up to here. Every year I get their height.
What is it at?
Huh?
What is it at roughly?
About right here. So my older daughter just turned 4.
she becomes taller than you.
So it's gonna go, I've already.
Yeah.
My wife is 5'9".
You're safe then.
And, no, my younger daughter is like 95th percentile for height. And if that holds, she'll be 5'11". So I definitely have
You're gonna have a couple more tattoos.
Thank you. See you guys.
I just forgot to turn the.
So that's going on a lot though. Do you not check cameras very much?
I do, but then I like. Okay, I'm not do it,
Okay.
and completely lose my brain. at the moment.
Can you send me a hard, sorry, not hard copy, a image or
Yeah.
whatever that?
The file.
Uh-huh.
Somewhere. Would.
Oh, I'll just put it on hands. That's fine. Yeah, Canvas is not like web work that locks down after the due date.
Okay, thank you very
Yeah,
much.
I thought only section 2.5 was due last night, so I couldn't do 2.6. Is
Okay.
there any option to do it late or something?
Yeah, absolutely. Ron, your name again?
An office?
No, okay, yeah, I will, let me give myself a note. When I get home, I will open it up. How much time do you need?
I'll do it by tonight.
Okay, I will open it for to the end tonight.
Thank you very much.
Yeah, of course.
Absolutely loved today's class. Thank you
Okay,
very
good,
much.
good, thank you.